This video is going to be a little bit different than the other videos in this playlist. We're looking at applications of integration, volumes, arc lengths, and surface areas. Now, in the other videos in this playlist, we went through each of these separately and in detail. This video, we're just going to look at a couple more examples. So I would suggest that this video, you look at the question, you see if you can do it yourself, and then compare your answer, because if you followed the playlist, then up to now you've already got a lot of instructions. So this is not necessarily instructional, it's just examples. If you just stumbled on this video, I will link the playlist down below. So what are we going to look at now? We're going to look at all of these things. We've got a lot of formulas for areas, volumes, and so on. What we're going to do is use the calculus and use the formulas we've looked at to confirm that the formula we have matches calculus. So let's take a look. For a circle, we're going to look at the area and the circumference formulas. A sphere, which is linked to a circle, as we've seen before, we're going to look at volume and surface area. So these are the formulas that we get on a standard formula sheet. For the length of a straight line, we've got Pythagoras. And then for a cone, we've got the volume and the surface area. So we're going to look at an example of each of these to match the calculus and the formulas we've derived from using calculus with these standard formulas that we learn long before we learn calculus. So let's get started. We start with a circle of radius 5. So here's my circle, the radius is 5. What I've got is, looking at the circumference of the circle, the circumference, 2 pi r. My radius is 5, so the circumference should be 10 pi. We're going to confirm that. The area of the circle, pi r squared, is 25 pi. Now, a sphere with radius 5 has a volume of 4 over 3 pi r cubed, so that gets us to 500 over 3 pi, and the surface area of the sphere is 4 pi r squared, which is 100 pi. All right, so let's get started. Use calculus to show the circumference of a circle with radius 5 is 10. So now I know my circle has a circumference, as a radius of 5, so that's 5 and that's minus 5. Now, the arc length formula that we derived earlier in this playlist is given there. So what we need to know is what function is represented by this half circle. Now, the reason we're looking at a half circle is because a full circle is not a function. But that is y equal to the root of 25 minus x squared. So that's my function. Right. In this formula, I'm going to need the derivative of this function. What's the derivative? Well, it's 25 minus 5x squared to the power of half. So it's a half 25 minus 5x squared to the power minus a half. So 1 over 2 root 25 minus x squared. And times the derivative with the chain law. And then we've got minus 2x. So this derivative is minus x over the root of 25 minus x squared. All right, and we're going to look at squaring the derivative in our formula. So if I want my circumference, now here I've got a half circle. So the circumference of my circle, this arc length formula is going to give me half the circumference. The arc length formula will give me the length of the half circle, so my circumference is twice that, 2 of them. So that is the integral from minus 5 to 5. The beauty of the symmetry of this graph is we can even go from 0 to 5, and 0 and 5 are sometimes easier to substitute in, but anyway, we can go from 0 to 5 and multiply it by 4 because a circle is so beautifully symmetric, but it'll all come down to the same thing. So let's go from minus 5 to 5. The square root of 1 plus the derivative of the function square. So if I square that, I get x squared over 25 minus x squared dx. Now, as it stands there, it's pretty ugly. We need to do something with whatever's inside that root, because none of our standard integrals can help us with that. So that's 2 times the integral from minus 5 to 5 of the square root. Let's put that in one term. I've got 25 minus x squared. Then my numerator will be 25 minus x squared plus x squared. So that gives me a 25 dx. The square root of 25 is 5. The 5, I can take the constant to the front, so it's 2 times 5, so I've got 10 times the integral from minus 5 to 5 of 1 over the root of 25 minus x squared dx. So what we have here is one of the standard integrals of arc sine. So that is 10 times, we're integrating now, so it's 10 times arc sine of x over 5 to account for that 25, between 5 and minus 5. All right, so that is 10 times arc sine. If I substitute 5 in, I've got 1, minus arc sine. I substitute minus 5 in, I got minus 1. Now, if you remember what arc sine looks like, the graph looks like this, where it goes from minus 1 to 1. That value is pi over 2, and here I've got minus pi over 2. So arc sine of 1 is pi over 2, arc sine of minus 1 is minus pi over 2. So I've got 10 times pi over 2 minus pi over 2. So it's 10 times pi, and that is 10 pi. So we've shown we're getting the same result as we did with the formula. Now we're going to use calculus to show that the volume of a sphere with radius 5 is 500 over 3 pi. So the first thing we need to remember is that I get a sphere by taking this function, y equal to the root of 25 minus x squared. If I take this function and I rotate it about the x-axis, then my resultant shape is a sphere of radius 5. So we're going to use that formula to see if we get the same volume. So we're using calculus and we're saying it's the integral from a to b of pi times the function squared. Now if I square that function, I just get 25 minus x squared dx. A and b are minus 5 and 5. So there we go. I can take the pi out. That's the integral from minus 5 to 5 of 25 minus x squared. But I know the antiderivative of 25 minus x squared is 25x minus a third x cubed, between 5 and minus 5. So we've got pi times, substitute 5 in there, and I've got 125 minus a third, 125, so that gives me 250 over 3, minus, substitute minus 5 in, and I get minus 250 over 3. So that is 500 over 3 times pi, which is exactly what my traditional formula got me. All right, now the same thing, we're looking at this half circle, but we're looking at a surface area of a sphere. So if I rotate that half circle, the surface area of the sphere is calculated with this formula. So I've got from minus 5 to 5. I know my function is the root of 25 minus x squared. I'm going to need the derivative. I've already seen in the arc length section, this is minus x over root of 25 minus x squared. And we already saw in the arc length section that if I've got 1 plus that derivative squared, that gets me to 1 plus x squared. If I make it one term, I get 25 over 25 minus x squared. So let us see. Using calculus, the surface area is then going to be the integral from minus 5 to 5 of 2 pi times the function, which is the root of 25 minus x squared, times the square root of 1 plus the derivative square. So the square root of 25 over 25 minus x squared, everything dx. Let's take the constants out. I've got a 2 pi and there's a 25. The root of 25 is 5 times 2 pi. That gives me a 10 pi. Integral from minus 5 to 5. I've got the root of 25 minus x squared times 1 over the root of 25 minus x squared, which gives me 1. So that one very quickly collapsed into something very simple. So the antiderivative of 1 is x, so I've got x between 5 and minus 5. So 5 minus minus 5 is 10, so I've got 10 pi times 10, which gives me 100 pi, which my original formula gave me. So we're happy with that one. Now we're moving on to the area of a circle. Now, this one takes a little bit more time. Now, before we even looked at integration techniques, we looked at what the definite integral means, and we looked at, if I look at the definite integral from minus 5 to 5 of this function, 25 minus x squared, it gives me, because the function is a positive function, it gives me the area under the curve. So if I want the area of a circle, I know it's pi r squared, so it'll be 25 pi. So if I calculate the area of this half circle and double it, I will get the area of the circle. So my area is going to be 2 times the integral from minus 5 to 5 of my function, which is the root of 25 minus x squared dx. Now note, I could have gone from 0 to 5 and just said 4 times that. That is why circles are very beautiful and symmetric, so we can look at that as well. But I'll stick to what I've got here. Now, the reason I left this one for last with the circle examples is we're going to have to use trig substitution. Now, if you don't remember trig substitution as an integration technique, I'm going to link those videos below, so you've got to make sure you can do trig substitution. So what we're going to say, we're going to say let x be equal to 5 sine theta. dx is then 5 cos theta d theta. But I must be very specific and choose my theta between minus pi over 2 and pi over 2. Why? So that sine can be a one-to-one function, so I can work with arc sine. And later on, we're going to need cos to be positive, so that will happen in that interval. Now, this is a definite integral, so I'll have to change the limits of integration. So if x is minus 5, to find theta, it'll be arc sine of 5 over minus 5 over 5, so that's minus 1. And that's minus pi over 2. If x is 5, theta is arc sine of 1, which is pi over 2. All right, we saw that earlier with the graph of arc sine. So we've got 2 times the integral from minus pi over 2 to pi over 2 of the square root of 25 minus 5 sine 25 sine squared theta dx, which is 5 cos theta d theta. All right, let's take the 2 and the 5 to the front. So I've got 10 times the integral from minus pi over 2 to pi over 2. Under the root, I can take the 25 out, and I've got 1 minus sine squared theta times cos theta d theta. Root of 25 is 5, so I can take the 5 out. So I've got 5 times 10 is 50. All right, now the integral from minus pi over 2 to pi over 2 of, I've got the root of 1 minus sine squared theta. 1 minus sine squared theta is cos squared theta. The root of cos squared theta is the absolute value of cos theta. But I know that the absolute value of cos theta is just equal to cos theta, since cos theta is positive on the interval minus pi over 2, pi over 2. Greater than or equal to 0 on the closed interval. So this gives me 50 integral from minus pi over 2 to pi over 2 of cos squared theta d theta. All right. Now, this is a long one. Now we need to use the half angle identity for cos squared. So cos squared, I'm going to flick backwards and forwards a little bit. This area is then equal to 50 times the integral from minus pi over 2 to pi over 2. And I had cos squared theta, but cos squared theta is a half 1 plus cos of 2 theta d theta. Take the half to the front, I've got 50 over 2. The antiderivative of 1 is theta. The antiderivative of cos 2 theta is plus a half sine 2 theta between pi over 2 and minus pi over 2. Now if we look at sine, we've got pi over there and minus pi over there. So this gives me 50 over 2. If I substitute theta in, I've got pi over 2. If I substitute pi over 2 in the theta, pi over 2 into this part, this term gives me 2 times pi over 2, which is pi, and I know sine of pi is 0. minus, if theta is minus pi over 2, sine of 2 times minus pi over 2 is sine of minus pi, which again is naught. So that's what we've got. So this gives me 1 pi. So I've got 50 over 2. I could have divided that a while ago. 25 pi. Is that what we wanted? Yes. That is what our quick formula gave us, but we've now used calculus to confirm that. All right, now we're moving on to the straight line. So let's take a straight line from 0 to 5. X-axis, y-axis up to 2. Now, that straight line, using Pythagoras, we get the length of root 29. That's the quickest way to calculate it. We're going to confirm that root 29 with the arc length formula. Then when I take the straight line and I rotate it about the x-axis, I get a cone. The radius of the cone, this part will be the 2. The height of the cone will be 5. So if I use my formula I've had on my formula sheet for years for the volume of a cone, we should get 20 over 3 pi. We will use calculus to confirm that, and same with surface area. We can calculate it, and we're going to confirm that. So let's get started. Straight line. The length is root 29. Pythagoras told me I want to believe Pythagoras. But I'm going to just use the arc length formula just to show that Pythagoras knew exactly what he was talking about. So let's take a look. This function, what's the equation of this function? It's a straight line going through the origin. The gradient change of y over change of x is 2 over 5. So it's 2 over 5x plus 0. The derivative is then 2 over 5. And if I square the derivative and add 1 to it, I get 1 plus 4 over 25, which is just 29 over 25. All right, so let's look at the arc length. The length of that straight line is the integral from 0 to 5 of the square root of 1 plus the derivative square. So square root of 29 over 25 dx. Well, that's a constant. I can take it out. That gives me root 29 over 5, because the square root of 25 is 5. The integral from 0 to 5 of 1 dx. That's root 29 over 5. The antiderivative of 1 is x, between 5 and 0. So we're just going to, x is just going to be 5 minus 0, which is 5. So that gives me root 29. So we're happy to see that we agree with Pythagoras. If we didn't, we would be wrong. Next one, the cone. The volume of a cone, the easy formula we learned long ago, 20 pi over 3. Let's look at the volume formula that we derived and see that we get the same thing. From a to b, so it's from 0, integral from 0 to 5. From 0 to 5. Because we've taken that straight line y equal to 2 over 5x, and we're rotating it about the x-axis. And that resultant shape is a cone. So the volume of that rotation is going to be integral from 0 to 5 of pi times the function squared. So that's 4 over 25 x squared dx. So 4 pi over 25 I can take out. And I've got the integral from 0 to 5 of x squared dx. That's a nice integral, 4 pi over 25 times a third x cubed between 5 and 0. So that's 4 pi over 25 times 125 over 3, which gives me 5 times 4 is 20 pi over 3, which is exactly what we wanted, so we're very happy to see that. Then the last one, the surface area of the cone. Now, the formula we get from our formula sheets is the whole outside area if I had to paint this whole cone. But this formula we derived from calculus gives me the surface area of the shape that I get if I take that line, y equal to 2 over 5x, I rotate it about the x-axis, but it gives me the outside surface area of the resultant shape. So that whole area. It does not look at the base, yet the formula on my formula sheet looks at the whole thing. So if I want all of it, and that's why it gets a bit technical, the question might say including the base, just to let you know, but this formula in general, if we use it, it just gives us the outside. But let's say we want to match it to the formula sheet formula, so we want to add the base. So that surface area, let's start with the base. The area of the base, this is a circle with radius 2, so it's 2 pi r squared, so that's 4 pi. Add to that. Now I use my formula. I'm going from the integral from 0 to 5 of 2 pi times my function, which is 2 over 5x, times the square root of 1 plus the derivative of the function square. But I already know from a couple of pages back that's the root of 29 over 5. All right, you can go back and confirm that if you did not get that. So what have we got? I've got 4 pi plus, let's take the constants to the front. That's a 4 pi over 25, and there's a root 29. Let me not forget about that one. The integral from 0 to 5, and I'm just left with the lonely x. But we like that because it's nice and easy to integrate. So I've got 4 pi plus 4 root 29 pi over 25 times antiderivative of x is a half x squared between 5 and 0. 4 pi plus 4 root 29 pi over 25 times 25 over 2 minus 0, so it's 25 over 2. And what are we left with? We're left with 4 pi. This goes into there once, twice. So we've got plus 2 root 29 pi. We can take 2 pi out as a common factor, and we're left with 2 plus root 29, which is exactly where we want it to be. So I hope this was helpful. I hope you tried these yourself and you used calculus and you could get these integrals right and these values. Thank you.